We begin Unit 3. Unit 3 is titled Energy and Society, and it begins at Chapter 5. Chapter 5 is titled Work, Energy, Power, and Society. So a few new terms in this title that we need to learn. Section 5.1 deals primarily with work. So work is a physical quantity. We're familiar with the everyday expression work, so we have to be able to adopt this new definition and use it. The definition of work is applying force on an object that displaces the object in the direction of the force or a component of the force. The symbol for work is W, and it's a scalar quantity, so it does not include a direction. The unit of measure, we're talking about applying a force onto an object and displacing the object. So we have newtons and meters. The unit for work is the Newton meter, and we define 1 Newton meter as 1 joule. So 1 Newton meter is equivalent to 1 joule. So to clarify, a joule is the work done by a force of 1 Newton over a displacement of 1 meter. And here we have the equation for work. Work is equal to F cos theta delta D, where F is the force in newtons, delta D is the distance measured in meters, and theta is the angle between force and distance. So certain activities are classified as mechanical work. In order for work to be done, 3 conditions must be met. The first condition states a force must be exerted on the object. The second condition is the object must be displaced by the force. So imagine pushing on an object like a large table. You can push on that object all day, but if the object is not displaced, then you've done no work. So condition number 2 states that the object must be displaced by the force. Final condition number 3 is that at least part of the force must be in the same direction as the displacement. So let's take a look at sample problem number 1. How much mechanical work does a store manager do on a grocery cart if she applies a force with a magnitude of 25 newtons in the forward direction and displaces the cart 3.5 meters in the same direction? So in this question, we're given force, and we're only concerned with the magnitude of the force, 25 newtons. We're given a displacement of 3.5 meters forward, but for the calculation, we're only concerned with the magnitude, and that's 3.5 meters. The question is asking us for work, and we know that work is equal to F cos theta delta D. We also need theta. So theta is described as the angle in between the force and the displacement. So we have force in this direction, forward, and displacement in this direction. So my question to you is, what is the angle in between the force and the displacement? So there can be an angle in between the force and the displacement. In this case, they're in the same direction. They could be in opposite directions. They could be at right angles to one another. But in this case, they're in the same direction. So what is the angle in between them? 0. So we can begin to sub and solve. We have 25 newtons for our force. Now in a different color here, I'm going to choose the cos of 0 degrees, and then our displacement we said was 3.5 meters. I want us to take a look at the cos of 0 degrees, and I want us to remember this. If we punch this into our calculator, we get the cos of 0 degrees is 1. And this is the case all the time. So whenever a force and a displacement are in the same direction, we know that this center value here, cos of 0, is always going to be 1. So we can simplify this. This is 25 newtons times 1 times 3.5 meters. So it's as if the cos of theta didn't even affect our answer. If we punch this into our calculator, what do we get for the work done? So to two significant digits, 88 joules. In the next example, sample problem number 2, we have a young man who is vacuuming. In order to do so, he's applying a force of 50 newtons at an angle of 30 degrees to the horizontal while he displaces the vacuum 3 meters forward. So the force that he's applying is at an angle of 30 degrees from the horizontal. This is the force. Now the third condition for work is that part of the force has to be in the same direction as the displacement. So right now, this is not pointing in the same direction as the displacement. So the displacement is in this direction, whereas the force is at an angle of 30 degrees from this direction. So what we need to do is break this force up into two component vectors and choose the component vector that is in the same direction as the displacement. So we could have this component and this component. We'll call this one horizontal x and the vertical y. So which of x and y is in the same displacement or the same direction as the displacement? X. So we need to determine the magnitude of this component, the x component. And this is where we use trig. We know that x is the adjacent to the hypotenuse, which in this case is f, and the angle in between the adjacent and the hypotenuse is 30 degrees. Adjacent hypotenuse forms the trigonometric ratio cosine. So we can set up this statement. X over f is equal to cos 30 degrees. If we solve for x is equal to f cos theta, cos 30 degrees. Now if you remember, this is part of the work equation. F cos theta allows you to determine the x component of the force. So that third criteria is built into the equation. So this example, we can solve it. We want to find the work done when we apply a force of 50 newtons as we cover a distance of 3.00 meters when theta is 30 degrees. We know the equation is F cos theta delta D, and we can sub and solve. So we have 50 newtons times the cos of 30 degrees times 3.00 meters. If we punch this into our calculator, what do we get for the work done? Keep your answer to 3 significant digits. Good. 130 joules, if we have to write that in 3 significant digits, it becomes 1.30 times 10 to the power of 2 joules. Perfect. Sample problem number 3. A worker lifts a 3 kilogram box vertically upwards 95 centimeters from the floor. He then walks across the room and sets the box back down onto the floor. So we have an individual who lifts a box with an upward force to a displacement of 0.95 meters. They tell you the mass of the box is 10 kilograms, but they don't tell you the mass required to lift this box. In order to lift a box with a mass of 10 kilograms, you'll need to overcome gravity. So the force of gravity acting on this box can be determined. 10 kilograms times 9.8 newtons per kilogram. It's 98 newtons. So the force of gravity acting on this box is 98 newtons. In order to lift this box, you have to apply a force of 98 newtons. So we can calculate the work done while lifting. F cos theta delta D. Force is 98 newtons. We have the cos of 0 degrees because they are in the same direction, and a distance of 0.95 meters. If we punch this into our calculator, the work done to lift this box 0.95 meters is 93 joules. In the second part of this question, we're taking this block and we are moving it to the right. It's important to know that even if you are moving something to the right, like a box, if you are lifting a box and moving it to the right, the force that you apply is still up. So the direction of the force required to move a box left or right is still in the upward direction. And you still have to overcome gravity. So we'll be lifting this box up and moving it to the side. They don't tell us how much we're going to be moving it. What is the angle in between the force and the displacement in this question? Good. It's 90 degrees. Now I want you to tell me, and do this in a different color so we remember, what the cos of 90 degrees is. 0. And this is always the case. The cos of 90 degrees is 0. So when we're determining the work done in this question, work is equal to F cos theta delta D. We know that since theta is 90 degrees, cos of 90 degrees is 0. Doesn't matter what our force is or what our displacement is, what will the work done be? 0. So whenever the force and the displacement are perpendicular or at an angle of 90 degrees from one another, the work done is 0. In the third situation, we're going to take this box and lower it back down. Now we have to remind you how this works in real life. So we want to bring it back down this distance, 0.95 meters. But what direction will we apply our force? When you're lowering an object, you're actually applying a force in the upward direction. So if I lower this binder, I'm still pushing up on the binder when I lower it. You're not pushing down on the binder from the top, you're actually lowering it by pushing up from the bottom. So in this case, the force is up and the displacement is down. So what will the angle in between the force and the displacement be? 180 degrees. So I want you to, in your calculator, type in cos of 180 degrees. And the answer is -1. This is always the case. So when we calculate the work done, work equals F cos theta delta D. That is 98 newtons. We said the cos of 180 is -1. And the distance is 0.95 meters. So the work done is -93 joules. So this is an interesting statement. When we raise the box, we do 93 joules of work. And when we lower the box, we do -93 joules. So take those two situations. The box starts on the ground and it ends up on the ground. So at the end of the day, it's as if you've done nothing to the box. So your total work done is 0. It starts on the ground and it ends up on the ground. And mathematically, this makes sense to us because we lift it at 93 joules, where the cos of 0 is 1, and then we lower it at 180 degrees, where the cos of 180 degrees is -1, with a work of -93 joules. So mathematically, it works out as well. So that leads us to two important summaries. The first one is, whenever the force and the displacement are in opposite directions, the work done is negative. The second statement, whenever the force and the displacement are perpendicular, or 90 degrees, the work done is 0. There's another way we can calculate work. We can calculate work from a graph. If we have a force versus displacement graph, we can calculate the work done. We have one such example where we're applying different forces over different distances. We've labeled these intervals A, B, C, and D. In order to find the work done, the work is equal to the area under the graph. So you can calculate the work done in each of these intervals. I want to take a look at just one of these intervals. We'll look at interval B. Interval B forms a rectangle under the graph, so I want to determine the work done for this interval. Determine the length of this rectangle and the height of this rectangle. Multiply them together, length times width or length times height, to determine the area of the rectangle. And what is the work done? 12 joules. So if you know the shape of the area underneath the curve, you can find the work done from a force versus displacement graph. Please try the homework questions to test your knowledge.